All right, this is physics lesson 4.1. We're going to be learning today about forces and the idea of net force. Here we go. The title of this unit is actually Forces and Newton's Laws. Newton's laws all pertain to forces. So for this to make any sense to you, you need to learn what a force is. So here we go. Force, symbol for force is a capital letter F. And as I think I've told you before, a force is just a measure of a push or a pull on an object. And because it is a measurement, we need units. We can measure force in either what are called pounds, I'm sure you've heard of pounds before, or newtons. All right, both of these things measure force. Newtons are our preferred one because they're metric. All right, but I want to make sure you understand that these measure force. So when I tell you that, for example, I weigh 150 pounds, what I'm telling you is that if you wanted to lift me, that would require a force of 150 pounds. Which should make sense, right? You need more force. You got to push harder to lift something that's heavier, right? So in America, we usually measure our forces in pounds. The metric system prefers newtons. So if we were to use the metric system, that example would have worked like this. I would have said that I weigh 150 pounds. Sorry, try that again. I would have said that I weigh 750 newtons, which is the same as 150 pounds. Which would have meant that to lift me, you'd need a force of 750 newtons, which is about the same as 150 pounds. All right, those numbers are not exact, but it's an approximation. Okay, so as it says down here at the bottom, we'll be using newtons because they're metric. All right, so examples of forces. There's a bunch of different examples of forces. Here are some of the more common ones. Force of gravity comes up all the time. Symbol for force of gravity is Fg. Oops, let's try that again. Symbol for force of gravity is Fg. Please remember, gravity always pulls stuff down towards the center of the Earth or whatever planet the object is on. Gravity does not push or pull up or sideways. Gravity pulls stuff down. Okay? Secondly, people can push stuff. We're going to see this all the time. So, for example, you might have the force of Roy or the force of Carl or whatever. And so you'll just label it with capital F and then a subscript, either the person's initial if there's no confusion, or for clarification, you can just write out the person's name. All right. This next example is a little bit weird. Stuff can push stuff. So you can have, for example, the force of the table. Okay. You presumably are sitting maybe at a desk right now watching this on your computer, and you've got a notebook, which you're hopefully taking notes in, and that notebook is not falling right now. The idea is it's sitting on the table. Gravity is pulling it down, so there's a force from gravity pulling the notebook down, but the table is pushing it up, preventing it from falling. All right. And then finally, force of friction. I'm not going to say too much about this right now, except that you need to understand that friction is in fact a force that occurs anytime two objects either are sliding across each other or attempting to slide across each other. And it comes from the contact of the molecules of the two objects. Even the smoothest object, if you view it through a microscope, is going to be sort of bumpy. If you look through an object through a microscope, it looks like sandpaper, kind of. And so if you imagine trying to rub two pieces of sandpaper together, the sand from one piece is going to push the sand on the other piece, making it difficult to slide them across each other. Friction is the same thing, except instead of pieces of sand pushing against each other, it's the molecules of the two objects that are sliding across each other. All right. Maybe the most important thing you need to know right now is friction always acts in the opposite direction the object is sliding in, or if it's the case where you're trying to move something but failing to because of friction, friction works in the direction opposite the direction you're attempting to slide it in. Okay? So anyway, there are some different examples of forces. So probably the best thing to do now would be, oh, I'm sorry, I skipped ahead. A few important things you need to know about forces. First of all, if Roy pushes a box with a force of 5 newtons, that's a measure of how hard he's pushing the box and doesn't tell us anything about how fast the object is moving. Okay, remember, it's possible to push an object without the object moving. I think in a previous video I had you stand up and push the wall, right? You can push the wall with a lot of force, push the wall very, very hard, but still not get any motion out of it. Okay? Please do not make the mistake of saying that something moves at 5 newtons. That doesn't make any sense. You push something with 5 newtons. If you want to talk about it moving, then you're talking about velocity, which would be measured in meters per second. Okay, so you can say you push it with 5 newtons, or it moves at 5 meters per second. And those are two different concepts. One is about how hard you're pushing it. The other is about how fast it's moving. Okay. Remember, it's possible to push an object one way while it's moving in another way. If you imagine something rolling forwards and you try to stop it, maybe like a heavy shopping cart or something, if it's rolling forwards and you try to stop it, what's going to happen is it's going to be rolling forwards while you push it backwards. And for a brief amount of time, it'll still be rolling forwards and slowing down because you're pushing it backwards. Okay. Please note, similar to displacement and velocity, force includes direction. So Roy can push a box with 5 newtons to the east or with 5 newtons to the west. Okay. And because of that, force can be negative. Okay. 5 newtons to the west would be written as negative 5 newtons, and 5 newtons to the east would be written as positive 5 newtons. All right. And finally, when we're doing calculations and making drawings, which we're going to talk about here in a minute. All right, sorry, there was an announcement there. Let's see, when doing calculations and drawings, we can treat a push exactly the same as a pull, as long as we think about what direction the object is being pushed or pulled in. In other words, here's the important part down here. In other words, pushing a box to the right with a force of 5 newtons is exactly the same as pulling it to the right with 5 newtons. Okay, so if you imagine a car stuck in the mud, whether you get behind the car and push it forwards with 5 newtons or get in front of it and pull it forwards with 5 newtons, as far as the car is concerned, that's exactly the same thing. Okay, okay, so let's do some examples here. What's going to happen is, because you're talking about objects in motion, there's 2 numbers that you're going to be concerned with. There's the velocity and the force. I'm going to try to always draw my velocities in blue and my forces in red. So here's an example of that. It says a very heavy shopping cart is rolling west towards Roy's car at 6 meters a second. Okay, so there we go. That's velocity, right? Because it's meters per second. All right, so what I'm going to do is I'm going to represent that by drawing what's called a vector. It's basically a fancy word for an arrow. Okay, and when I draw the velocity vector, I'm going to draw it so that it's not physically touching the object. So the shopping cart is here at the center of the screen. Notice I drew this blue arrow below it and not touching the shopping cart. All right, and I made it pointing to the west to indicate that the car is going to the west. And I'm going to label it velocity equals 6 meters per second. And to further emphasize the fact that it's moving west, I'm going to make it negative, because west is a negative direction. All right, now there's another piece of information here too. Roy is attempting to push it with a force of 20 newtons. Okay, now since he's stopping the cart, think about which way he's going to have to push it. If the cart is rolling now on my screen to the left, to stop it, we'd have to push it to the right. Okay, so when you draw force vectors, when you draw these force arrows, the arrow always needs to start in the object and point out. So I'm going to put a dot in the center of my object, and the arrow is going to point out from there. That red arrow that I just drew represents a force because it starts inside the object and points out. And then I'm going to label the force. This is important. A lot of people skip this step. Label it. It's the force of Roy, and it's 20 newtons. Okay? These drawings are crucial this chapter. Okay? So what we've just learned is 2 things. We've learned how to draw a velocity arrow or a velocity vector. That's this guy down here. Notice it does not touch the object, and it points in the direction of motion. And here we've drawn our force vector that does touch the object. It must point out of the object, not into the object. It points in the direction that it's being pushed or pulled, and you have to label it. Okay? If this had said pull instead of push, the drawing would have been exactly the same. Okay? So here's another example. Roy is driving to the Lady Gaga concert. Unfortunately, a large cow is standing in the road. So Roy pulls the cow to the west with a force of 50 newtons. Make a drawing. Okay, so the cow is standing. That's telling us information about the velocity. It's telling us the velocity is 0. Now, since he's not moving, I'm not going to draw an arrow, because which way would I make my arrow? He's not moving in any direction, so I don't draw an arrow. Okay. Now, there's a force of 50 newtons from Roy pulling it to the west, right? So I'm going to put an arrow that points out of the cow to the west. I'm going to label it force of Roy, negative 50 newtons to indicate how much force he's pushing with. All right? So that is how you draw forces and velocity. All right? Please keep in mind that there could be, depending on the situation. There could be other forces on the cow. You know, maybe there's friction or whatever, but based on what we know so far, I'm just trying to help you understand how to draw forces and how to draw velocity. And so that's what we've done there. All right. So here we go, net force. This is going to be a huge concept this chapter. So that is why I've taken a whole slide to write this down. Net force is the total of all the forces on an object. Okay. So if you want to find the net force on an object, what you're going to do is you're going to list all of your forces. So maybe you've got force number 1 and force number 2 and force number 3. To calculate net force, you just add them all up. Okay? So, you know, if there's 100 forces, then you're going to add them all up. If there's 2 forces, you're going to add them up. If there's no forces, then your net force is just 0, right? Because there's no forces. Okay? So this is your first new chapter, or first new equation for this chapter. Please write it down, put big stars around it, draw a smiley face, because smiley faces are fun. That is super important. Okay? I'm realizing now I'm going to go over on my time. We got to make some drawings here, and these drawings do take a little time, so I apologize. This video is going to run more than 15 minutes. So I will shoot for 15, though. Here we go. So what we're going to do now is a few examples. What I'm going to do is give you some different scenarios of different types of objects, and we are going to make a drawing and find the net force. So in example 3, a large refrigerator sits at rest in the center of a room. Make a drawing and find the net force on the fridge if A is Roy pulling it to the right. So what you're going to do is you're going to draw your object. There's the refrigerator. Okay, it's sitting at rest. So that's telling me information about the velocity. So I'm going to write V equals 0. And then I'm going to identify all my forces. In this case, Roy is pulling it to the right. So Roy pulls it to the right. So there's Roy pulling it with 8 newtons. It doesn't seem that there are any other forces on it. So in this problem, my net force is simply 8 newtons, right? Because that's the only force on it. So that is my drawing for that one. Roy pulls it to the right with 8 newtons. Okay. Now, in B, it's the exact same thing, except it says pushes. So because of that, there's no other difference, pushing and pulling. Okay. So the idea is it's the exact same as A. Okay. Again, it does not matter whether it's being pushed or pulled. What matters is the direction. And in both cases, my direction is right. And that's the important part. And that is why this arrow points to the right. Okay? So let's move on and do another example. Example 4. A large box is sliding to the right across a frictionless floor at 5 meters a second. We're going to, again, make a drawing and find the net force on the fridge in each of these two situations. So in A, Roy is pushing it to the right with 8 newtons, and Sally's pulling it to the right with 12 newtons. Okay? So once again, we're going to draw the box. Okay? It's sliding to the right at 5 meters a second. So that's a velocity, right? 5 meters per second is a velocity. So when I draw my velocity arrow, remember, it does not touch the object. I'm going to label it velocity equals 5 meters per second. So there's my velocity. Now on to the forces. It says Roy pushes it to the right with 8 newtons. So here's my force of Roy, 8 newtons. Sally's also trying to make it go to the right. She's pulling instead of pushing, but again, what's important is the word right. She's got a force of 12 newtons. So watch how I do this, you guys. This arrow, I'm going to draw it a little bit longer because it's more force. Okay? The length of the arrow is the length of a vector is important. The longer you draw the arrow, the longer you draw your vector, the more force or velocity or whatever you're indicating. Okay? So that's that. Now we've got to find our net force. So our net force, this is still part A that I'm solving here. Our net force is the total of all of our forces. So for us, it's the force of Roy plus the force of Sally. So it's 8 newtons plus 12 newtons, and it gives you 20 newtons. Okay, the two of them are working together, so their combined force is 20 newtons. That's your net force. Okay, so let's do part B here. Boom. All right, so in part B, the main difference is this time, instead of them both pushing it to the right, like they did in A, in part B, they're going to both push to the left. All right, so how does that affect it? Well, let's see. Let's draw our box. It was still sliding to the right at 5 meters a second, right? So I'm going to draw my velocity, 5 meters per second. And I need my two forces to go to the left this time. So it's just going to look like this. Here's my force of Roy, -8 newtons this time. Here's my force of Sally, -12 newtons. I don't know if this confused you. I don't care how you draw your arrowheads. You can draw them like this, you can draw them like that, whatever, it doesn't matter. Just put an arrowhead on there. Okay, and then find your net force. So the net force is the total of all the forces. In this case, we got Roy, we got Sally. So we're going to have -8 newtons from Roy, -12 newtons from Sally. Add them up and you get -20 newtons. Okay, again, they're working together, but this time to push it in a negative direction. Okay, I think this next example is our last one. We're probably looking at 17 minutes here by the time we're done. So example 5, a box is sliding to the left across a frictionless floor, and we're going to make our drawings. So here we go. Part A. So here's our box. It's sliding to the left, so I'm going to draw my velocity in. Again, I'm using blue for velocity. It's -4 meters per second. Oops. Because it's going left. And then let's draw in our forces. Let's see. Roy's pushing it to the right. So here's our force of Roy, 9 newtons. And Sally's pulling it to the left with 15 newtons. Notice, make the arrow a little bit longer. Okay, so now they're working against each other. Roy is trying to push it to the right with 9 newtons. Sally's pushing to the left, or pulling to the left, with 15 newtons. So the idea is they're working against each other. Okay, who's going to win? Well, Sally is. She's got more force, right? How much more force? The difference between 15 and 9 is 6 newtons, right? So what's happening is all of Roy's 9 newtons get canceled out by Sally's 15 newtons, leaving us with a net force of -6 newtons. Mathematically, it's this. Again, this is still part A. Net force is the force of Roy plus the force of Sally. So we've got 9 newtons from Roy, 15 newtons from Sally. Don't forget the negative sign. Add it up and you get -6 newtons. Okay? So that is exactly the same. What's happening in this problem is exactly the same as if only one person was pushing it with 6 newtons. Okay, so in other words, in terms of what the box does, this is exactly the same as this. Okay? All right, so let's do part B. Oh my gosh, I'm sorry guys, this is way longer than I hoped it would be. Let's do part B. Here's our box. It is sliding at 4 meters a second. Ooh, I hope I made that velocity negative in the previous example. If I didn't, I should have. All right, so this one, Roy is pushing to the left. Oh, phooey. I made this example wrong. I'm going to make a correction on this example here. I wanted one of these two forces to be to the right. All right, so in this example, we've got Roy pushing it to the left. Force of Roy is -18 newtons because he's pushing to the left. And then Sally's pulling it to the right. So now force of Sally is +18 newtons. What are those two forces going to do to each other? They completely cancel each other out, don't they? Right? So the idea is our net force is force of Roy, force of Roy plus force of Sally. So you get -18 newtons plus 18 newtons, and you get a net force of 0. This is exactly the same as if nobody was pushing the box at all. Okay? So that is how you make force drawings. We'll learn a little bit more about them later on. And how you find net force. It's the total of all of your forces. All right? Now, as I went through this, I gave you guys some rules. I'm going to really quickly. Here are the rules for drawing force vectors. If you want to pause the video now and jot those down. I'm not going to read them because you can read. And then once you're done with that, here's the rules for velocity vectors. Okay? All right, I apologize for this video being so long. I really thought this was going to be short, but I was wrong. I'm going to hit stop. You should have a good day, and I will see you in the next physics class.